Hello class, this is Dr. Viv. Let's look at a typical Newton's second law problem in two dimensions. I have here a fixed wedge and two masses riding upon it connected by a ideal string. Ideal means it doesn't stretch and it has no mass. The object on the level surface has got mass little m, and the object on the inclined surface of angle theta has got mass capital M. At the moment that we start to look at this problem, we observe that the masses are moving to the left with a speed v. That is to say, M is moving along the incline and capital M is moving up the incline with a speed v. We have to solve for two things, the acceleration and the tension. Newton's second law should be used. Newton's second law says the sum of all the forces is equal to mass times acceleration, where little m stands for either this mass or that mass. Now this can be broken up in two dimensions as two separate equations. The sum in the x direction is equal to mass times acceleration in the x direction, and similarly for the y direction. Now in this problem, the x and the y directions are not unique to both the masses. As a matter of fact, it's good policy to take the axes to be independent for both of them. So the natural system for the mass little m would be the traditional x and y axes. Y-axis up, x-axis to the right. Now the reason I pointed to the right is because I know, even without really deeply thinking about this problem, that the acceleration must be to the right. This must slow down because the mass m drags on capital M, drags on little m, eventually causing the velocity direction to actually reverse. So first it'll slow down, stop, and then reverse. So now even if you did not know that, it doesn't matter. You just pick an arbitrary direction of acceleration and you pick your x-axis to be along that direction. So let me write my acceleration and my velocity. The convention we have for drawing what are called free body diagrams is that you must draw the object with a heavy dot and then write the forces. The forces should be drawn with some consideration for what's already known to happen. So we know that this mass doesn't fly off the table, so we can expect Fn1 and mg, the force, normal force Fn1, and mg, the gravity force, to be equal. Then there's of course the tension force F sub t. Now this picture, if nothing else, should convince you that the acceleration is going to be to the right, because Newton's second law says wherein there's an unbalanced force, there must be an acceleration. There's an unbalanced force along the x-axis, so there must be an acceleration along the x-axis. And once you have an acceleration a, the acceleration of the other one is automatically fixed because the string is remaining taut. That is to say, it's got tension at all times. So you have to take into account that, and for example, you cannot have this acceleration pointing like this and this acceleration pointing like that, because that would lead to the absurd conclusion that these two masses are going to meet. That doesn't happen. By the way, this is an ideal pulley, which means it's got all the properties of an ideal pulley. It's got no mass, no friction, and so forth. Let's just make sure that we need to find the acceleration and the tension. And I also want to investigate some limits. That's a useful thing to ask. I'll talk about that at the end. Now for the other object, the appropriate coordinate system is not this one, because this object is on a slanted surface. So I'm going to draw a separate coordinate system that's tilted at an angle. Now in this coordinate system, you've got to be very careful about the angles. So gravity always acts straight down. That's the nature of gravity, because the Earth's center is somewhere here. The normal force, being the normal force, is always perpendicular to the surface. So that's going to be Fn2. Now what is this angle theta? That angle theta is actually this. Observe that this is 90 degrees. So if that angle is theta, this is 90 minus theta. And because this angle is 90 degrees, this angle is also theta. Now let's draw the remaining forces. There's only one more force remaining, and that's a tension. That's the mass capital M, that's the mass little m. So we have drawn the two free body diagrams. I also find it convenient to draw a table. The table will have as many entries as there are forces, so it's going to be a table with 3 entries. This is going to be the name of the force. That's going to be the x component of the force, and that's the y component of the force. So the first force is the force of tension. X component of tension is Ft, and y component of tension is 0. The second force is the normal force. X component 0, y component positive, Fn1. Lastly, gravity, x component 0. I'm just looking at this diagram and reading it off. Y component negative mg. The table faithfully reproduces whatever you've drawn in the free body diagram. I'm making a slightly bigger table for this because I see sine theta and cosine thetas coming up. Just 3 forces again. Let's go down in the same order. Tension. The x component is actually negative Ft according to my coordinate system. The y component is 0. The normal force 0, and Fn2. Gravity. Now remember, cosine is adjacent, so the y component is going to be cosine, but negative. So that's going to be negative mg cosine theta, and the x component actually is going to be sine with a positive. So we have finished filling up the table. Once you've filled up the table, writing Newton's law is simply knowing how to read the table and copy things down. So at this point our work is almost done. Newton's law for this particular object m can be written: sum of all the forces in the x direction is equal to mass times acceleration in the x direction. Well, that translates into the equation f sub t, because that's all the sum. It's f plus t plus 0 is equal to m times a. Let's call that equation 1. Then we have sum of all the forces in the y direction, which is equal to may by Newton's law. What's that going to be? Now from experience, we know that the block does not fly off the incline. So ay is 0. That we have to put in by hand. Fn1 minus mg is equal to 0. This is where I like to say an alien would not be able to do this, because an alien does not have any experience of this situation, but you do. So this gives me Fn1 equals mg 2. Let's go ahead and do the same 2 equations here. Sum of all the forces this time equals capital M times ax. That's giving me negative ft, but there's also an mg sine theta, and that's equal to ma. Let's solve this. Well, actually, let's just keep it like that. Let's call this equation 3. And then last equation is going to be sum of all the forces in the y direction is equal to capital M times ay. Once again, we are superior to the alien because we know this is 0. So I get Fn2, which is the sum of these two things in the column, minus mg cosine theta equals 0, which can be written as Fn2 equals mg cosine theta. Let's call that equation 4. Equation 2 and 4 merely express the burden felt by the table. Not too interesting. What we are interested in finding is the acceleration and the tension. Those come from equations 1 and 3. Actually, this system is rather easy to solve compared to the other systems we see in class and the homework. So all you've got to do is take the f sub t here and put it in there. So from 1 and 3, I get the following. Negative little ma, so I've substituted for f sub t, plus mg sine theta is equal to ma. And now I add little ma to both sides. So I get mg sine theta is equal to m plus m times a. And now I divide both sides by m plus m. That immediately gives me the acceleration. The acceleration is mg over m plus m times sine theta. So we've solved the first part of the problem. To find the tension, you have an option of either using this equation or this equation, but I can bet dollars to the donut that nobody will choose that. You will just choose this. So f sub t is equal to m times a, so that gives me little m times capital M over m plus m times g sine theta. I have purposely put this quantity, the product of the two masses divided by the sum of the two masses, in a separate parenthesis because it's a very important quantity in two-body problems involving Newton's second law. This object is called the reduced mass. Which I'm going to indicate by the symbol mu red. The unfortunate thing about the symbol mu is it's used for too many things in this course. It's used for mass per unit length. It's sometimes of a string in the later part of the course. Then in week 5 or something, we'll be using this quite a bit for friction. In fact, mu, if I just wrote it as mu sub r, it could be thought of as a rolling friction coefficient. So that would be very dangerous. That's why I wrote mu red. And mu written by itself can stand for either the static or kinetic friction coefficient. So unfortunately, the symbol mu has been used too many times. Except for COVID, I think. There's no mu variant as far as I know. So anyway, the reduced mass mu red is given by that. And it follows this really interesting rule. 1 by mu red is equal to 1 over m plus 1 over m. So this type of addition is sometimes called harmonic addition. Those who have studied a little bit of electrical theory will realize that this is how resistors in parallel add, or capacitors in series also add like this. A lot of things in nature add like this. So the last part is limits, as I promised. So let's take a couple minutes to look at the limits. The only limit I can think of that actually is interesting are the angle limits. So let's look at limit of theta equals 90 degrees. Theta equals 90 degrees simply corresponds to this mass m hanging off a cliff. So theta equals 90. I'll draw a separate picture for it quickly. It would correspond to this picture. It's one of the problems we did in class. So we call it the modified Atwood machine, MAM, of the first kind, I believe. So anyway, there are several kinds of Atwood machines. So modified Atwood machine of the first kind. Let's look at what happens when theta is 90, sine theta is just 1. So the acceleration is mg over m plus m, and the tension is just the reduced mass times g. So that gives you the maximum values of those things. The other limit is theta equals 0 degrees. Think about what that means. Theta equals 0 simply means that these two objects are on one single plane connected by a string. Well, what do you think? If that's the situation and the plane is frictionless, then if the object is moving to the left with speed v, it will continue to move forever with the same speed v by Newton's first law. So the acceleration is 0 as predicted, and the tension will be 0 too. There's no reason for there to be any tension because there's no acceleration, so the two blocks are actually staying in sync and the thread serves absolutely no purpose.